immediately surround it. But then we have the absolute extrema, which are the overall highest and lowest values in the set. So that's what we're going to investigate here. So we have all these relationships here, but you're going to see a lot of similarity between this and what we just did. And that's fine. You know, the key is seeing what that relationship is in terms of the context of the problem. So, you know, it's kind of a vague statement, but it is what it is. So we have this function, this I just lost the word there. It's multivariable function. I don't even know why I drew a blank there. We need critical points. Right. So first thing we're going to do is the same thing we do for every other problem. We're going to differentiate. So f sub x 2x minus 2, f sub y 2y minus 6. Right. We'll get the critical values first before we dive into anything else. So set it equal to 0. You get x equals 1. Set it equal to 0. And you get y equals 3. So we have critical values, but we're looking for, ultimately, we're looking for extreme values. All right. So my criticals, 1, 3, and f of 1, 3. We have some bounds here that we have to account for. All right. So those bounds could lead to extreme values because, you know, you take a look at this and you say, okay, well, 1, 3. You know, if you're just plotting along this graph, you could say I got 1 in this direction, 3 in that direction, and then something, you know, some value corresponding to that that's on the surface. So probably right there. That looks like it could be the lowest point on the graph, right? But what about the highest? Well, it depends on how far on the graph you're allowed to go. This could be the highest. You know, depending on perspective, maybe this is the highest. I don't know. It isn't until I explore those boundaries that I really get a good sense. So that's what we're going to do. We're going to look at the boundaries. Okay, so one boundary is the line x equals -2. Another boundary is x equals +2. All right. Another boundary is actually a point, specifically -2. Well, it's the corners. Actually, I'll get to the corners in a second. So another boundary would be y equals 0 and y equals 4. All right. So what we do is we redefine the function. Instead of being a function of two variables, we're holding one of the variables constant at whatever the boundary value is. In this case, -2, +2 with 0 and 4. Right. So if I replace x with a -2, I'm going to get a function of y. So plug a -2 in for x, I'm going to get 4 plus y squared plus 4 minus 6y plus 14. Clean it up. Y squared minus 6y plus 22. If I'm not mistaken. All right. Desmos, good resource when it comes to this. You just use the A's and B's. You know, I'll leave Desmos out of it for now. But you just use the A's and B's and then just see what you get. You know, so we're looking at, yeah, so -2 squared is 4. Negative 2 times negative 2 is positive 4. That comes together to give you an 8 plus the 14 that's already there is going to be 22. Everything else stays put. All right, we do the same thing with an x value of 2. Now maybe we'll just move this stuff off to the side, bring this down. So we're going to have an f of y. Still plugging and chugging away. So 4 plus y squared minus 4 minus 6y plus 14. Result, y squared minus 6y plus 14. All right, because the 4 and the negative 4 cancel away. So then we could do the same thing just with the x's. So I'll just move this down here. Move them both collectively up a little bit. So we'd have f of x, y squared minus 6, I'm sorry, x squared minus 2x plus 14. $16 plus what? I keep doing it. I keep putting them in for x. X squared plus 16 minus 2x minus 24 plus 14. So it looks like x squared minus 2x plus 6, 30 minus 24.
Professor, quick question. On the first boundary, x equals to negative 4, why is that plus 22?
When I replaced the x with a negative 2, I got a 4. When I replaced this x with a negative 2, I got a positive 4. And then I had a 14 here. So 4 plus 4 plus 14.
So you got the 2 times negative 2 times 2, right?
Negative 2 times negative 2.
Yeah.
Okay.
Yeah. Okay, gotcha. Thank you.
No problem. So we have all these functions, and they're going to correspond to extreme values also, right? They're going to have little max and min values of their individual domains, both figurative and literal, right? But we also have to test the corners, right? So the corners are any possible pairings of the values that make up the restriction. So negative 2, 0. I'm going to write the ordered pairs first, and then I'll get the triple value in there. So negative 2, 0, negative 2, 4, positive 2, 0, positive 2, 4. All right, so these would be the corner values evaluated for the original function. All right, so those are the possible corners that we could have, and each one of those could correspond to an extreme value. All right, so out of all of this stuff here, the critical values, the boundaries, and the corners of the restricted areas, we have candidates for the absolute max, absolute min. All right, and so that's what we're going to do. We're going to investigate. All right, but it's going to involve a fair amount of number crunching. And so that's where Desmos becomes the most handy. So I'm going to type it in as S equals, put it in any way you want, but I'm using S equals A squared plus B squared minus 2A minus 6Y plus 14, minus 6B. All right, benefit of doing it this way is we can make use of the sliders. So we get a 4 for the critical value. So 1, 3, 4. For these points, -2, then 0 gives me a 22. Then a 4. Gives me a 14. Then I'm going to do it with a +2. Gives me a 6. So 2, 4, 6. And then 2, 0, 14. All right, so we could start kind of like diagnosing a little bit here, because if I'm looking for the lowest and highest values in the whole set, maximum, minimum values, I'm looking for the largest and smallest z values. All right, so this is a set of possible candidates. Let me do it this way. All of these guys are fair game. All right, we also have to take care of the boundaries in a sec, but we'll get to that. The smallest value that I have here is 4. The largest value I have here is 22. So these are all out, right? These are not going to be absolute extrema, right? So I don't have to worry about those points, right? I just have to take care of the boundaries now. Now, the good thing is, well, one of the good things is that they're all quadratic. They're functions of one variable, right? So I can just put in a standard form quadratic. You know, I can do it as a new Desmos if I want. And so I'll save this. This is absolute extrema. I spelled it wrong, but whatever. I'm going to put it in as f of x equals ax squared plus bx plus c. The benefit of doing it this way is you don't have to retype every single time. You're just manipulating sliders. All right. What I would want is extrema, right, from this. So for a parabola, the extrema ends up being your vertex. So what we can do is create a vertex model. You get some quotes in here, if I can find them. No, I'll just do it the old-fashioned way. So vertex. So we would have the coordinate -b divided by 2 times a, comma, f of -b divided by 2a. And it'll label up the vertex for you, which is great, right on the graph. So I just need to go back and take a look at these values, 1, -6, and 22. I'll just up my maximum value, I'll make that like 30. So I want to get to 22. So 313, right? So the vertex here is 313. That's a y value corresponding with a z value. All right, that's not the biggest number and that's not the smallest number, so that's out. All right, so then 1, -2, 14. Is corresponding with a 113, the vertex 113. That's an X against a Z. "13" again, not the biggest, not the smallest, so that's no good. 1, -6, 14 is what I'm looking for next. Went the wrong way first. 3, 5. I have a smaller value, a 4, because again, this is the Y value against the Z value. I have a smaller Z value. The smaller Z value is 4, so this is out. And then finally 1, -2, 6. Gives a 1, 5, so same deal. That's X against the Z. So it appears as though our absolute maximum is going to be 22 and our absolute minimum is going to be a 4, right? And that's only because looking at this information, looking at this graph and comparing our critical value to all other possible points that could be candidates, that leads us to this. This is our only possible outcome, all right? So fortunately, we kind of drove the point home without having to get into the second derivative test, right? So we didn't have to verify that the critical value was a relative minimum because comparatively it's smaller than all the other numbers, so we knew it had to be a minimum. Right? The only other possibility would be that it's a saddle point where it's neither the highest nor the lowest, right? So highest in one direction but lowest in another direction, you know. But that's not the case here either. So what we can say is the absolute min is 4, absolute max is 22, but only on that interval. And that's the thing. This kind of problem is a very specific type of problem. It only works in cases where you have a restriction in your domain and range. Right? So this has to be given to you. Otherwise, it's just an ordinary second derivatives test.